Okay, here we go. A spotlight is 30 feet away from a wall. A man walks at a speed of 5 feet per second against the wall. If the spotlight stays on the walking man, at what rate is the spotlight rotating when the man is 40 feet from the path closest to the spotlight? Sometimes you need a visual to be able to make sure that you know what stuff is, and your book does lay that out for you. This is actually an example very similar to what your book puts forth in this section. I draw my 4 sections. What do I put in the first box? The picture. Oh. When is the showing? 7 or? Good boy. Oh. All right, no. Well, we'll take care of the Hobbit piece tomorrow. Let's do this. Okay, I'm going to call that theta. A man is currently standing 30 feet. The question says, at what rate is the spotlight rotating? So anytime you see this type of rotation piece, you need to make sure that you're considering theta. Theta is what is changing in this situation. This will be definitely new learning, but the problem I ask you on your assignment is identical to this, okay? So we need to make sure that we follow this piece. Is this changing at all? No. It's 30, okay? I'm going to call this X. I'm going to call this Y. And now we need an expression to talk about some of the changing pieces, okay? I want to know at what rate theta is changing. Any ideas? Sine of theta does equal X over Y. Do we know anything about Y? Are we trying to find Y? No. We're trying to find the rotation of the angle. So let's just start with this then. Let's forget about the Y. What trigonometric ratio expresses a relationship between X, 30, and theta? Tangent. Very good, yes. So I'm going to write this. Tangent of theta is equal to, as Greta said, opposite divided by adjacent. What's the opposite side? X divided by 30. Okay? So what I can now do is I'm going to solve for X. 30 tangent of theta is equal to X. Do we know X prime? At what rate is he walking? 5. Do we know theta prime? That's what we're solving for. X is changing, theta is changing. What's the variable that's not on the board that's changing? Starts with T, time. So we take the derivative with respect to time of my equation, which is 30 tangent of theta is equal to X. Boys and girls, boys and girls, boys and girls. This is something that we need to be very, very careful of, okay? Because this is the confusing part. When you take the tangent of theta, you often say, well, I'm going to take the derivative of, theta, and I'm going to get derivative tangent of theta, you're going to get secant squared of theta. That's as long as you're taking the derivative with respect to theta. But we're taking the derivative with respect to time. So if you're taking the derivative with respect to time, what's the derivative of theta? Theta prime. So anytime the derivative of the inside is not 1, you must use the chain rule. Say it again. Okay. If I was taking the derivative with respect to theta, the derivative of tangent of theta is just secant squared of theta. We've covered that, right? However, when you're taking the derivative with respect to time, what's the derivative of theta? Theta prime. Anytime the derivative of the inside is not simply just 1, you need to make sure that you use the chain rule. So let's set up the chain rule. What's the, for this part right here, what's the outside? 30 tangent of u. What's the inside? Theta. What's the derivative of 30 tangent of u? 30 secant squared of u. What's the derivative of theta? Theta prime. So when you multiply that together, you get theta prime times 30 times secant squared of theta. So you got to make sure that you use your chain rule. Equals, yes, take the derivative of x, you get x prime. Very good. Okay, so I'm going to write that right here. We got 30 theta prime secant squared of theta equals x prime. What are we solving for? Theta prime. Do I know x prime? What is x prime? 5. Do you know the current theta? No. Can I figure it out? Yes, I can. Because I know that this side is 30 right here, and the man is currently how far from the path? He's currently 40. So this is my current situation. This represents the present time. So I can now use tangent, inverse tangent. Very good. So let's grab our calculators. What do we need to make sure we're working in? All right. It's a fractal. Mode, we are in radians. Tangent inverse. Boys and girls. Tangent inverse of 40 over 30. And I get 0.927. 0.927 radians. Yep. Yes. Yep. You could work in degrees. I'm going to choose to work in radians. That's the common reference that we use here. So that's just the point. There is no label. That's how we know it's radians. Okay, so now we have 30 times theta prime of, I need to take secant squared of 0.927. I don't have a secant button on my calculator, so what do I do? Right. 1 divided by parentheses cosine of 0.927. And I got to square that, right? And I get 2.78. Are you having fun with Morgan and Aaron? I don't know. Colleen Thompson likes to creep on my presentations. So. Okay, there we go. We got 30 times theta prime times 2.77 is equal to 5. I can now yes. Well, we did 1 divided by cosine squared. Divide by 30, I get 0.06. So x prime equals 0.06 radians per second. Oh, theta prime, theta prime, theta prime. Yep. Thank you. There we go. That tells us that this angle, the angle is changing, so the angle is rotating at that instant at a rate of The man's walking and the spotlight stays on him. Yep. Skip the kite when we go to the backside. You guys, we get at 11:37. We'll do the kite problem at the beginning tomorrow, and Monday you will have time to work on your study guide and any assignments. That's where we're at. So we draw the picture. It says two sides of a triangle are 15 and 12 centimeters in length. The angle between them is increasing at a rate of 0.04 radians per minute. At what rate is the area increasing when the angle is 60 degrees? So I'm going to draw my picture. I have a triangle. One side is 15. The other side is 12. Are those sides changing? No, they're not changing at all. Is theta changing? Is the opposite side changing? Yes. Fortunately, I don't have to know the opposite side. Do you know the area of a non-right triangle? Yes. Yes, but if it's not ever changing, we can generally plug it into our initial conditions, which are this. The area of a triangle is equal to 1/2 AB sine of C. Maybe you remember that from trigonometry. And what that really means is 1/2 times 2 sides times the sine of the included angle is really what it means. Now, if these are changing, then I can't plug anything in for them. Is the length of this side changing? No, so I can plug in 12. Is 15 changing? No, so I can plug in 15 for B. Is C or my angle changing? So I can't plug it in. So what I have is area is equal to 1/2 times 12 times 15 times the sine of C. What's 1/2 of 12 times 15? 90. And I'll call it theta because we wrote it there. We're solving for theta prime. Or I'm sorry, we're solving for area prime. It says at what rate is the area increasing when the angle is. Okay? If I take the derivative of this expression, will I get an A prime? Yes. What is the other thing that's changing that's not on the board? Time. So I take the derivative with respect to time of A equals 90 sine of theta. Yes, I do need to use the chain rule again, but you guys, when we do that, what do you think is going to pop out front? The theta prime. So the derivative is actually very easy. We get A prime is equal to 90 theta prime times sine of theta. I'm sorry, cosine of theta. Yes. Yes. So we're solving for A prime. We don't know it. As Berkey just said, we know that theta prime is 0.04. Do you know theta? Do you know what theta currently is? 60 degrees, but that's in degrees. Converted to radians? Pi over 3. Raji. All right. So let's do this last part then. We have 90 times 0.04 times the cosine of pi divided by 3, which you guys all know is 1/2 anyway. We get 1.8. Because the current angle is 60 degrees, 60 degrees when converted to radians is pi over 3. Area prime is equal to 1.8. What is my unit of measurement? Radians? Radians per minute. Oh, yeah, you guys are misleading me. It's 1.8. The area is increasing in centimeters squared. There you go. Your area is increasing, therefore it has to be in centimeters squared. The angle is radians per minute. I'll give you guys two problems that model that you can work on. They're identical to that, okay? Boys and girls, page 204, 24, and 25. Part of the problem is that as you look at these problems, well, 24 is actually like the kite problem. We just didn't have time to set it up. So 25 is identical to the last one. You could try 24, but we will do that beginning tomorrow in class. Once again, two problems. That's it. Finish up your other related rates problems. 25 is the one we did today. I do have, again, your study guide on the back table. It's the calculus study guide. You do have a stapler. You're out of here in 5 minutes. First question to Berkey.